Hey guys, what's going on? Today I will try to answer the question of how do we know what molecules look like? So, simple answer, it boils down to a mix of chemistry and spectroscopy. I would say chemistry gives us the most hints of what a substance is composed of, and spectroscopy sort of fills in the details. I spelled spectroscopy wrong. Let me erase it and spell it right. Spectroscopy. So, you gotta use a little bit of common sense too. Imagine you have a substance and you throw it in fire and it explodes. Well, using common sense, you know that things that are metallic and shiny, usually when you throw those in fire, they don't explode. So, therefore, you can pretty much erase most of the periodic table and assume none of those atoms are in your substance. You can pretty much focus on the first 2 or 3 rows of the periodic table and be like, okay, I know my substance is composed of atoms in these 3 rows. And, similar experiments to that, you can very nicely narrow down what is your molecule composed of. So, what we're going to do is start by assuming we know everything in the periodic table. So, let's assume we know the masses of all the atoms. Masses of atoms and how much electrons each atom has. Number of electrons on the neutral atom. So if you take one electron away, your atom's going to be charged, but we're dealing with neutral atoms here. Okay, so we will assume that for this whole video. And I already said, chemical reactions give us the biggest hints. Give us the most hints. So they give us hints of what something is composed of, or the atoms that thing is composed of. Now, we'll talk about if we can't think of an experiment to where we can perform a chemical reaction and know what atom is in our substance, well, we can use heat. Chemists been using heat since, they were called alchemists. So, you can heat a molecule, very, very high temperatures, and the atoms in that molecule will disconnect themselves and break into atoms. So you heat molecule very high and break into atoms. And now you take those atoms and you can do various things with them. So one thing you can do is atomic spectroscopy. Now, if you could manage to get all your atoms to just have one electron, then you know that the energy of light that your sample is going to absorb is some constant, times 1 over some quantum number squared minus some final quantum number squared minus some initial quantum number squared. So different atoms are going to have different energies of these. Oh, well, you got to add your charge in there too. That gives you a big hint. And for multi-electron atom, these atoms emit very sharp lines in the spectrum they produce, and each atom has its own spectrum. So let's say you start with a pure atom. You know the atom you got is gold, right? And you throw that gold sample into an atomic spectrometer, and you measure its spectrum, and now you keep that spectrum as a reference. Now you get some unknown thing, and you heat it up real high, and you put that into an atomic spectrometer. If all the gold lines are there, you know your thing has some gold in it. So, now we're getting somewhere. So, that was a little bit about atomic spectroscopy. Other spectroscopy is really useful. One is called nuclear magnetic resonance spectroscopy, or NMR. This works by a principle similar to what they use on MRIs in hospitals. But I won't talk about that. I won't talk about how this works. I'll just say NMR, it tells us which atoms are connected together. And it mostly does this because the properties of hydrogen atoms or protons. So hydrogen atoms, which are H atoms, are very good at feeling their environment. They can feel their neighbors very good, you know. Imagine they have really long arms and they're blind, and all they can do is feel. Well, they have really long arms and their touch is very sensitive. You know, like a blind person feels someone's face and can recognize them like that. Well, hydrogen atom kind of does that. Feels its neighbors. And another method is mass spectrometry. Now, strictly speaking, this is not a spectroscopic method. It's a spectrometric method. And there's fine details, which I won't talk about, why they're totally different. I mean, there's no light involved in spectrometry. That's basically the difference. So, imagine you got a molecule, right? Imagine your molecule is a hexagon. And you can break that atom by shooting high energy particles, such as alpha particles at it, right? So imagine, you know, your alpha particle goes there and breaks that. And now you got a piece like this, and it's, you know, it lost an electron, and this piece happened to gain an electron. Now you take those pieces and you shoot them out of a gun. And once you shoot them out of the gun and produce a stream of particles, well, you take a magnet, not a magnet, but you might be able to use a magnet too. But you shoot that stream of particles through a capacitor. And I talked about this in previous videos. This is how J.J. Thomson discovered electrons. And since these things are charged, it's either going to... So this bottom minus charge piece will be deflected this way, and it depends on how much that thing weighs. And the positive charge will be deflected this way because it's attracted to the negative plate. And depending on where it lands here, so heavy atoms will land closer to the center, and lighter atoms will land farther and farther away because they're going to be easier to bend towards the plate which they're attracted to. So that can give you an idea of what pieces your molecule is composed of, how much those pieces weigh, how much mass those pieces have, and that's why it's mass spectrometry. Okay. Now some spectroscopies. Well, besides NMR. NMR is a spectroscopy. But some spectroscopies I've already talked about in previous videos. One is rotational spectroscopy. And rotational spectroscopy gives us the distance between the atoms. Gives bond distances. Okay? Remember, I wrote the equation that the rotational energy equals some quantum number J times J plus 1 over H times H bar squared over 2 mu R E squared. So E is the bond distance. Now if you shoot a bunch of different light at your atom and you happen to find a place where it does absorb that light, well, you know that energy of light's h nu. Well, you solve for Re, you get Re equals the square root of H bar squared over 2 mu E. And here we can assume J equals 0 if we have our thing at low temperatures, and that means our J equals 0 state is the most populated state. That's a pretty good assumption as you get colder and colder. Now, vibrational spectroscopy it tells us the strength between bonds. And in a previous video I said the energy is equal to h bar omega times some integer plus a half, and this omega part equals the square root of k over mu. Mu is the reduced mass, same as that mu. And let's say you're in the ground vibrational state, which is very accurate at room temperatures, so like 70 degrees Fahrenheit. So your energy will be something like this. And you know how much your atoms weigh, so K basically gives you an idea of the bond strength. And different bonds will have different Ks. So if you have a carbon connected to another carbon, say, that's gonna vibrate faster. Well, you gotta take the mu into account also. But that's going to vibrate faster than something like two heavy atoms connected together. So right below carbon in the periodic table you got silicon. So a carbon-carbon bond would be stronger than a silicon-silicon bond. But I think. But the point is, these different bonds will vibrate at different frequencies and therefore different energies. So again, you shoot a bunch of light and you see where that light is absorbed, and that will tell you which kind of bond you have. So for example, a carbon-carbon might absorb red light and a silicon might absorb blue light. Well, if your red light goes away, you have carbon-carbon bonds in there in your molecule. Okay, well that was a brief explanation of how we know what molecules look like, and I will restate that it's mainly a mixture of chemistry and spectroscopy, or chemistry and shooting light at your thing that tells you what your thing's made out of. So I hope you found that helpful. Thanks for watching and have a good day.